you all for being here. My name is Jack. I'm the container team lead at Scale Computing, working on Project Kraken. And with me is Dave Demlow, VP of Product Strategy. And together we are going to be presenting about containers and some of the stuff we've been working on, especially related to container distribution and Kraken and some of the features that you've already likely seen demos for. So these are the engineers on the team. That's Sam Caldwell and Ben Morrison. Please, if you see them, feel free to talk to them. They're awesome, and they are very knowledgeable about containers in this whole space, and great guys. So today we're going to talk about containers, runtimes, just kind of a 101, or what are containers, how do they fit into what we do on HyperCore, how does orchestration work, what does the ecosystem look like. We're going to do some demos that get into how do you deploy a single Docker container out to your fleet of clusters, how do you deploy Kubernetes. In this instance, it's actually single node Kubernetes with a couple of containers. We'll talk a little bit about GitOps and CI/CD, and we'll talk about the roadmap, which will kind of be sprinkled throughout. So just to pause for a second, we're going to be in beta for Kraken in Q3. So this family of features, zero-touch application deployment, we could really use some help if people are in organizations, whether you are using VMs as a primary means of getting your deployments and workloads out into the world, or you're already container native. Anywhere along that spectrum, you could help us provide some tremendous feedback that would make the difference in our development process for these set of features. So if you're interested and want access to the Q3 beta, please get in touch with Taylor at scalecomputing.com, and he'll get you the access that you need. Okay, so just starting at a 30,000 foot view of how we sort of frame containerized workloads at Scale Computing. On the left here, in the Scale Computing platform as a whole, you've got SE Fleet Manager. And SE Fleet Manager is really the control plane for your distributed fleet. It's the means by which you monitor and interact with your clusters through a single pane of glass. And in the middle here, we've got legacy applications, which for the purpose of this talk, we're sort of thinking of anything that's packaged and delivered historically as a virtual machine. And modern applications in this context are going to be synonymous with containers. So the important thing to take away from this slide is that today, with how we run applications on HyperCore, we support both containerized applications and traditional virtual machines. And there's a whole range of different modalities for getting those things set up on HyperCore. But let's talk about containers for a second, just from a theory perspective. So what is a container? Well, a container is really nothing more than a packaging format, fundamentally. It's a way to get your application logic and your dependencies bundled into a single artifact that you then distribute out as the thing that you deliver holding your application. And there's a few different ways and modalities that deployment target could take. Here's just a couple that we're going to focus on. And on the left here, we've got VMs. This sort of top gray layer here represents the containers. So it represents this combination of applications and dependencies, and they're sitting on top of a container engine or container runtime. And that's going to be a common component regardless of modality. You can't deploy containers without a container runtime. What makes this side on the left different is that there's a guest OS implying a VM, and that's sitting on a hypervisor. And this is actually how we choose to deploy containers here at scale, and I'll get into why and some of the nuances in a minute. The other modality on the right is bare metal containers, which is a modality that's gotten a lot of traction, and you hear it come up a lot. But this is just basically a situation where you have a container runtime. It's deployed to some operating system like Red Hat on top of some device, and you just deploy the containers to that runtime. So they're running on bare metal effectively. Now, the way we choose to do containers on HyperCore as VMs is how we enable those containers to adopt and sort of inherit the underlying resiliency properties of the HyperCore system. And just to touch on a roadmap piece of this for a second, it's our intent in the development of the Kraken feature set to start to progressively assume some of the responsibilities for maintaining that underlying guest operating system and leaving you in a position where you're more focused on the workloads themselves first and foremost. Now, I'm just going to make an architectural comment about to clear up a misconception that comes up with containers sometimes, which is a container does not, containerizing your application does not stipulate any particular architecture. So if you have applications that have been historically, like modular monoliths that you're deploying in VMs, you can take those applications, port them to a container exactly as they are, and that accrues to you some of the benefits of containerization without requiring you to re-architect your application. Once you've done that, of course, you might start to think to yourself, okay, well, maybe I want to break up some of the concerns here. So I want to extricate some of the modules, and maybe I want to, put them in different containers. And that's where orchestration tools like Kubernetes come in handy. So that'll be the focus of the next few slides.
Another word you might hear is microservices. Not
Right.
all containers have been split up into microservices. You can have monolithic containers and everything is all built into one app. Containers do lend themselves towards, refactoring your applications into microservices that are easier to maintain, easier to deploy, and so forth.
Definitely. They're not synonymous, in other words, yeah. So I'll talk about some of the tools in the space. If you've worked with containers at all, it's likely that you've worked with them through Docker. Docker is sort of like the original container runtime and tool set for working with individual containers. There are more recent players in that space. Podman is an example of a more like security conscious container engine. And these are like primarily focused on working with single containers. There are some like add-ons like Docker Compose or Podman Compose that let you sort of start to think of multiple containers as a logical unit that you can act on. But these are primarily development tools. They're just gesturing at a need for when I have more containers that need to work together, I need some way to tie them together. And clearly there's like a case for orchestration here. And so in production, if you do have multiple containers that have to work together and are kind of logically an application, this is where Kubernetes and orchestration tools come in. Now here at the bottom, Kubernetes is the only player that I'm listing in that space. It has really come to it is synonymous with container orchestration at this point. There was a point in history where there was like Apache Mesos and Docker Swarm and a few other contenders, but Kubernetes has completely eaten the space. And there's a number of benefits and consequences to that. But when we talk about orchestration, it's effectively synonymous with Kubernetes. Let's talk for a moment about Kubernetes and how we go from, okay, we've made the decision that we're going to use containerized applications. Now we want to translate those containerized applications into workloads running on some Kubernetes cluster on HyperCore. That journey is, Kubernetes does not think inherently in terms of containers. It thinks in terms of pods. And a pod is a logical connection or a logical collection of containers that share some configuration. It shares the same network namespace. It shares some storage, and maybe it's defined in a manifest that allows you to like specify replicas. So how many instances of this application do I want? And those pods get scheduled by the Kubernetes controller mechanism onto a variety of nodes. Those Kubernetes nodes in the HyperCore case are, of course, virtual machines. And it's this collection of nodes, worker nodes, control plane nodes, as may be the case, that forms the cluster. Okay, so we've got a Kubernetes cluster, which is a bunch of VMs running on top of a HyperCore cluster. And one important consideration here is that, at least in the HyperCore case, the topology really matters. So the physical distribution, that is, if you have all of your Kubernetes nodes, you have a 3-node HyperCore cluster, and all of your Kubernetes VM nodes are all stacked on a single node, and that thing goes down, you now don't have the high availability guarantees that you would otherwise have if you had kind of taken care of the distribution piece of it. And this is another area in the roadmap where, as we move into a more managed experience of Kubernetes and HyperCore, we'll start to subsume and take responsibility for some of these things, so that again you're focused primarily on the workloads and not the details of topology and distribution. So there is I've talked a little bit about like sort of the scheduling and the scalability and all of the benefits of Kubernetes with regards to lifecycle management. I think there's a really compelling reason to build your apps on Kubernetes today that is understated, and that is the ecosystem. So Kubernetes is, in my view, it sort of represents sort of the best thinking in distributed systems and in the open source world, kind of in one application. And there's just been, as a seed technology, Kubernetes has given rise to this explosion of innovation. And I would encourage anybody who's curious about the tools that are out there in Kubernetes to Google CNCF landscape. That's the Cloud Native Computing Foundation landscape. And the first result you'll get, it's actually this little tiny tile that says replace with link next to it.
Yeah, exactly.
But it's going to be hundreds of tools that solve a lot of like low-level distributed systems problems related to communication, databases, storage, things like that. And the benefit of having such a bloom of excitement and innovation and development in the space is that if you move to Kubernetes and you start developing your applications there, that enables you to sort of up level your thinking when developing your applications so that you're more focused on providing value rather than solving low level systems problems, right? So it's an incredible benefit to just be able to compose from open source solutions and start to iterate that way. This is the bullets on this slide are a bunch of flavors. I mean, Kubernetes has at this point, in addition to having all the tools, it's also has a bunch of distros. So there's K3s, they're like edge optimized flavors of Kubernetes. Talos Linux is a really interesting project. It's basically Kubernetes as the operating system. It's a personal favorite. We really like it.
And there's a session later this afternoon with Sodero Labs that'll go more into Talos Linux and their Omni control management platform.
Yeah. Microkate's Minishift, also resource-constrained environment optimized Kubernetes. There's a bunch of cloud-focused ones, managed offerings like GKE, AKS. All the cloud providers have one. There's a whole collection of tools that are sort of for taking a bunch of Kubernetes clusters and bringing them under common management and having them talk to each other if you need to. These are all based on service mesh technology, Arc, Google Anthos. There's a bunch of those. But as I said,
and by the way, all of these distributions have been run, can be run on HyperCore.
Right.
We can help make recommendations on your particular use case, but a lot of times you may have an application developer or your in-house development team has an affinity towards a particular stack. Maybe it's, they're using GKE in the Google Cloud, so they want to run the matched on-prem version that's most similar. So yeah, all of these are available to run on HyperCore.
Yep. We've even, for Kraken, we're starting to build up a library of reference applications where, we show examples of how you get various flavors out. Okay, so I'm going to hand it over to Dave. Dave's going to walk you through a demo getting containers out with Terraform, and then I'll take it over for K3s.
Yeah, so we've got a couple series of demonstrations. Here, I think we probably this was a late change. We recently announced a Terraform provider. It's in the HashiCorp registry. So I was playing around with that and decided, I'm going to deploy the container, deploy this VM and deploy the container using Terraform. We'll kind of go through in the demo. These are all steps that you can do manually. So, the demos here, we're going to do automation, kind of infrastructure as code type deployment, but this can be done manually and so forth as well. And in the demo, I'll show the cloud init, so we provision the VM, we pass it part of our API. You can pass cloud init into the VM, which is basically a list of instructions, how this VM should configure itself, set it up, what packages it should run, and so forth. And let's go ahead and dive into that. All right, so here we've got a HyperCore cluster. This is the location of the HashiCorp registry, and a quick just example of what a Terraform main.tf looks like. So you can see it basically, we say we want to use the scale computing HyperCore provider. We want to use, we have cluster credentials there, a URL and access credentials. We're going to pass cloud init information that I've stored in a separate template file. And then this point here is really, we're going to create this VM. We're going to clone it from a particular VM, pass that cloud init information in. And then here I'm showing the cloud init. And if you look at kind of that run command, these are the steps that if you wanted to do this all manually, you would basically do. Configure an Ubuntu or VM or Linux of your choice, set up a container runtime. In this case, I'm using Docker, so it's apt, get install commands to install Docker. And then at the very end, I'm running a Docker compose up file, a command. And also part of the cloud init is I'm passing in this Docker compose file, which you're kind of seeing here. And this is the instructions of this particular application is 2 containers. It specifies what ports I want to expose my application on and so forth. I do time lapse this, but I just ran a Terraform apply. And if we go to look to the cluster and speed, I put this in a loop. So it's actually creating 3 identical VMs. Here I'm logging in through the HyperCore console. You can see cloud init. So if you haven't messed around with cloud init, again, anything that you want to automate in your deployment to do consistently, you can put in that user data structure. Looking at the end of the cloud init configuration here, running a command of Docker PS. So in this case, my runtime is Docker. I'm just listing the specific containers and some of their configuration. And then part of what I did was I exposed the front end web service container for WordPress out on a particular port and connect into there. And then here I'm just showing that I actually in my provisioning, created that Docker Compose file. And that does also give me within the VM lifecycle management. So I just do a Docker Compose down, and I can take down that application. I could make changes to that Docker Compose file, Docker Compose up, reconfigure, like, if I wanted to change the versions of a particular container or whatnot. And so that's the particular demo here. So let me pass it back to Jack here. All right.
Very cool. So my next demo is actually going to be using some of the Kraken features that were demoed earlier this week. But instead, this time, we're going to be getting a single node K3s cluster with some workloads, Prometheus and Grafana, out to 4 edge locations. So we have the Fleet Manager cluster list, and we're clicking on the deployments feature, which is this Kraken mechanism. This is a deployment. This is a deployment that consists of target group. There's an application and a history of successful releases. That target group is 4 different clusters that we showed in the cluster list. But this is an example of a Kraken manifest. It's really just YAML with Cloud init and letting the system know that there's a virtual disk that it has to go out and download. And so here are the clusters that we're going to deploy to. None of them have any workloads running. So we're going to hit the deploy button here. And now there's a job per cluster. There's logs that are streaming back from each of those jobs. Pretty soon here, this is going to let us know that it's created the VM. Sure enough, on stores 1, 2, 3, and 4, the VMs are starting to show up. When we go back, we'll see that job finish up. As we go back to the list view, we'll see that all of them complete. And then we'll go to the VMs. The VMs, the QEMU guest agent is going to have to come online and initialize, but as they do, the IPs are going to show up here. As they show up, we'll go ahead and grab one of those IPs and navigate to the workload at the port that we configured. And there's the workload. So you define the application in one place, and you select any number of clusters, and you get it out to all of those locations through Fleet Manager. Here I'm just going in and showing that Kubernetes is running on the node, and that's the awareness of the Kube API for the node and the workloads. That's it.
Awesome. And again, so this kind of automated deployment could be done with any API-based tool. Can also be done manually. So you could do this with PowerShell using our REST API or our Ansible collection. Very soon the Kraken technology as well. So one of the things we wanted to talk about. So in that demo, we deployed a single node K3s cluster, and just like we have single node systems in HyperCore, and it's like sometimes they're called single node clusters. I will say for Kubernetes especially, and for a lot of the workloads we see in smaller locations and edge locations, maybe 99 out of 100 do not necessarily need the complexity of what you would get with a multi-node Kubernetes cluster. So in this case, those K3s single node virtual machines that we deployed already have resilience because they're running on HyperCore. They already have storage persistence. If a node, the physical HyperCore node they're running on dies, that VM is going to get restarted, restart the application very quickly. However, there are use cases where it does make sense and to deploy a multi-node Kubernetes cluster. We're not going to be able to get super deep into all of this, but I will show you kind of what that looks like and some of the tools that would be set to do that, and then some of the things that come into play there. So as Jack mentioned earlier, if you are running a Kubernetes cluster that's multiple Kubernetes nodes, each one of those would be a VM. You would want to make sure you manage the affinity, and generally you'll have 2 types of nodes. They can be combined depending on your configuration, but you'll have some nodes that are master nodes or control plane nodes that are kind of managing the Kubernetes cluster itself. And then you may have worker nodes that are separate. Sometimes those can be combined where you run pods on control plane nodes as well, but generally probably kind of best practice if you're deploying multi-node Kubernetes is to separate those. Each one of those would be virtual machines, and then you can use our affinity strategies to make sure that those are load balanced across the physical nodes. So For master nodes for Kubernetes, it is recommended you either want 1 or 3. You want an odd number. You don't want 2, for example, because they do have to maintain their own quorum capabilities. Um, when it comes to storage, first of all, a lot of truly refactored Kubernetes container or cloud native applications you might hear are generally stateless. So they may not have any persistent data that they need to store or maintain, or they may store those in some external a cloud storage or an object storage system, or just as files on an NFS server. All those things are valid configurations for Kubernetes. It is also possible, however, to set up Kubernetes to use local storage attached into a virtual machine. And it is smart enough that it knows if this particular application or this pod stored some persistent data on worker node 1, when that pod needs to be rescheduled, it knows it has to go on worker node 1 because that's where the data that it requires is located. So there are use cases for doing that. I mentioned usually if you do have persistent storage that needs to be shared, and you might even have, if you are building an application that's load balanced, it's running pods and with replicas across all the nodes behind the load balancer, they may need concurrent access to the data. So in that case, NFS, having an NFS server they can all access file storage on, or object storage. MinIO is a very popular object storage system. It emulates S3, AWS S3 storage. It can be deployed in containers. It can be deployed in VMs as well. So those are some of the storage options that exist. There are also essentially software-defined storage products and some open source stuff that can load inside Kubernetes clusters and kind of aggregate and manage persistent storage across those. OpenEBS is one. Portworx is a very sophisticated commercial project. Those could be run inside virtual machines if you needed that kind of Kubernetes managed storage capability outside of the VM persistent storage that we provide. Obviously, the downside here is the complexity. You've got a multiple VMs to manage. You've got the affinity to manage, more resource usage, and so forth. But it is an option to do. There are certainly use cases where it makes sense, and so we're not going to really go through a live demo here, but I'm going to show how this can be done and how this can be automated. In this case, we're going to use Ansible, and we have a Git repo that's here. It's a part of the scale computing called K3S on HyperCore. It's got scripts and examples and so forth that you can walk through, and basically from scratch. I mean, from the starting point of it will go and you tell it, I want to deploy these on Ubuntu 24.04, and it'll go grab those cloud images from the Ubuntu canonical sites and download those, create the templates, VMs, and so forth. So you basically, clone this, go through the steps. This may be hard to see, but this is kind of the key variables file where you define what that Kubernetes cluster would look like, and it's mostly giving it IP addressing, answering some questions about how many control plane nodes, how many worker nodes, do you want NFS storage deployed, and this playbook will automatically create those nodes, create those VMs, deploy an NFS server, connect all the various nodes into that. So and it'll even deploy apps, optionally set up MetalLB as a load balancer if you have Kubernetes applications that you want that. You basically let it run, it'll end up, and then you'll have basically something that looks like this on your cluster, and in this case, it'll label it, the agent nodes or the worker nodes there, the server nodes, our control plane nodes, and then you can also see there's a resilient VM that's the NFS server. So that entire set of virtual machines was deployed by that one playbook, more or less by filling in the vars file, the template with the IP addressing and what you wanted it to look like. And by the way, you can also use that to apply updates. So say you need to, there's a new Kubernetes version that you've obviously tested internally, and now you want to deploy out to production. You can go, and that's one of the parameters in that variables file that you can go and redeploy, and it'll go ahead and reach out. In this case, still using Ansible, using the APIs to connect directly into the VMs, directly into Kubernetes, and do that kind of day 2 management operations. And by the way, and then I guess this is the from logging in using kube control. You can see up at the top, I'm just doing a get nodes, and so you can see those are all this top section up here. Those are the IP addresses that I set. Those are all separate VMs. All the nodes are ready. After that, I'm just looking at some various applications and pods and so forth. And part of this script actually was also deploying some initial workloads on that. So, and this is probably at this point kind of the view that your developer teams would use if they wanted to get access into this particular cluster. They wouldn't necessarily know or care that it's running VMs or need any access to the HyperCore side. This is what they would be able to do to get access to the containers, to the logs, make changes, or so on and so forth there. We're doing great on time, so I think we'll have some time for questions. So in terms of roadmap, I think we've mentioned a number of these things, but one of the things beyond the initial release of Kraken is that we do have plans to incorporate and integrate basically a managed Kubernetes runtime. And so kind of winding back to that last Ansible section where I said, okay, I had to pick Ubuntu. I had to pick what K, in this case, I picked K3s as the distribution to deploy. I had to configure certain parameters and then go deploy a bunch of VMs. And now if I want to change that, I want to add nodes, I go back and do that all again. We do have plans to basically have a managed Kubernetes layer available through HyperCore. With a number of benefits. One is we'd be responsible for that operating system. You'd be able to tell us how to version it, how to update it, downtime windows, things like that. But we would own that, and you would really just need to care about giving your developers access to what do the applications look like, making changes there. As part of that, right now Kraken is focused on deploying the images, the disk files, the ISO files, creating the VMs and so forth. But as part of this managed runtime, where we can make some opinionated assumptions, we'll be able to also deliver updates to your application stack for your container-based applications. So you get cloud fleet management for those applications as well as the physical nodes and the virtual machines as well. And the benefits there are, from your standpoint, zero operating system maintenance. We're going to own that just the same way we update HyperCore and so forth. Easily scale and deployment. So if you all of a sudden decide, hey, we're deploying some new application, we need some new worker nodes, you just change your manifest and apply it. And we know we need to create some new worker nodes, and we need to scale them up and give them more RAM or CPU or things like that, so that you can focus on the applications and not the details. So a little bit of roadmap stuff there. And I want to thank everyone for your time.